Hello, everyone. Glad to see you. We have some new faces, some familiar people. I would ask you to stop your videos for those of you who have it on. So, because I'm recording this webinar just for your safety, yes? So our rule is that only me and our speaker have the video on. Okay, thank you. So today we have an absolutely amazing speaker and an absolutely amazing topic. Yes, Miche? So the topic is Martian minerals, an alien time capsule. And it is taught by Miché Aaron, who is a PhD student at Johns Hopkins University. I met with Miché at astrobiology conference 2 years ago, and you will see that it's very easy to make friends with Miché because she's so smart and witty and just fun to be around. You will see for yourself now. Okay, so now we will start the webinar and I will let Miché talk. So, but before that, I want to share with you some of our Zoom guidelines, okay? So, for those of you who are new. So please keep your camera and microphone off. Please feel free to ask questions in chat, but please stay on the topic, right? Please stay friendly to everyone in the webinar, yes? And please don't spam in chat. Don't repeat your questions twice. We will see them, we will answer them, we will get to them, I promise. But maybe not right away. So thank you for following our guidelines. And now I will stop sharing my screen and Miché will start hers.
Okay, so how's everyone doing? I hope we're all having a good day. Well, we're going to have a better day because we're going to be learning about Martian minerals, alien time capsule. And I'm really excited about talking about this because this is something that I'm studying right now as a PhD student at Johns Hopkins. So just to give you a quick outline of how this talk is going to go. First thing I'm going to talk about is who I am. Because many of you don't know who I am, but trust me, I'm a good person to know. And I love rocks, and I like Mars, and I love astrobiology. The next thing we're going to talk about is how can life form on Mars? So there's different processes, different formation patterns that could occur that would cause life to form overall. And these are things that we have to look at whenever we want to determine if or when life occurs. The next thing we're going to talk about is minerals can capture life. And this is something that's going to be pretty interesting because not many people know that rocks can hold information about life. And we'll talk about the different types of rocks that can do that. And then lastly, can light find life? So let's say there is life on another planet. How can we find it? Well, we just got to use what we have, and that's light. We'll talk about that too. But first, who am I? So my name is Miché Aaron. I am a third-year PhD student at Johns Hopkins University. So I just became a third year. I just started my third year at Hopkins, no longer a second year. My field of study, I study planetary geology, which honestly, I could just say planetary science because I study all different disciplines of science with regards to a planet. So the biology, the physics, the chemistry, and that all plays a role in geology too. I study IR spectroscopy, which, interesting word, IR is infrared, and that's a light that we cannot see, but we'll talk about that in a moment. And spectroscopy is the study of light. And of course, astrophysics, because when you're studying a planet, you have to know the physics of a planet. You have to know how it got to become a planet. And that's under the umbrella of astrophysics. And physics is the study of how things work. So how does the stars work? How does anything in space work? My favorite food is anything spicy. I love hot sauce on anything. Favorite color is lavender. I do enjoy crocheting, painting, playing video games, collecting rocks, collecting coins. I love stargazing, and I also volunteer at the Air and Space Museum. Well, when we're able to go back, I'll be able to do that more. But for now, I'm at home volunteering, and I still love it. Fun fact, I used to be a professional clown, and I had fun face painting and making animal balloons, and one of the things I enjoyed painting was, you can probably guess, stars and planets. And one day, once I'm done with school, I'm hoping that I can be in charge of my own planetary mission. So I can determine what we're going to study and how we're going to study it. That way we can make discoveries for the future of mankind, or humankind actually. All right, so in case you aren't sure what we're going to be talking about, or what planet or what celestial body we're going to be focusing on today, we're going to talk about Mars. And in case you're not sure what Mars is actually the fourth planet from the sun. So there's Mercury, there's Venus, there's Earth, and then there's Mars. And Mars is generally it's generally half the size of Earth. One cool thing that everyone really loves about Mars, and of course, first thing they notice about Mars is that it's red. And we don't really see a lot of red planets out there. Well, we don't have that many planets to compare it to, but this one's red. And if we were to go on the surface, we would see there are a lot of rocks. So this picture, a lot of people could think, oh, this is somewhere in the United States, or this is somewhere on our planet. This is actually on Mars. And it's funny that people would think that, because a lot of these rocks are basically made the same way like Earth rocks are. So what's the difference between our four planets here that we have? What's some differences that you guys notice?
You can answer in chat.
Answer in chat, of course. I will see it. All right. So someone says size, someone says color. Okay. Anything else? Color. Okay, more color. What about composition? Is there a difference? Shape? Someone said shape. Now, that's funny because size and shape are two different things. And this kind of goes into the realm of physics a bit more on how a planet interacts with another larger body. Say, for example, sun, or maybe something smaller, like a moon. A moon can affect the size of a planet, meaning that it can stretch it, causing it to be a bit more elongated, which means a little bit wider. So instead of it looking like a sphere, it's looking more like a football, but not really a football, just mathematically a football. But we wouldn't want to call it a football. So are all planets made of the same stuff? What do you guys think? Yay, nay, no, nah, no, no. Oh, that's very interesting. I'm seeing a lot of no's. So here's the thing. I didn't really specify what stuff is. So stuff in this case would be the elements. And a lot of planets in our solar system all came from the same solar system, right? It's kind of like how you and your brother or sister have the same parents, but you all look different, right? Well, you all have, but even though you look different, you still have the same DNA. And so if we look at this video, this is showing how our solar system was formed. And even though we have the rocky, solid planets closer to the sun, and yeah, physically they look the same, where further away, the planets out there are more gassy or icy. We still have the same elements. We still have the same chemical composition. And that chemical composition is basically like their DNA. And that still shows that they are all made of the same stuff. Even though they're different, they're still relatively the same. Let's see, there we go. So these are our planets in our solar system. So we have 8, we used to have 9, but unfortunately Pluto didn't make the cut. That's unfortunate though. And I would love to talk about why Pluto's not a planet anymore, and as much as I would love to, but that's probably a discussion for another talk. But in case you're really curious, Pluto doesn't have the right orbit. Its origins are relatively unknown, and I forgot what the third reason was, but for the most part, it doesn't have the right orbit. It tends to compete with Neptune and also other icy bodies out there in the further part of our solar system. And if it's competing for a spot, then that doesn't make it a planet. It's kind of difficult to make it a planet. But with each of our unique planets, they all have a different spin. So some spin really, really fast, like Jupiter. Look how fast Jupiter's going. So this is saying that Jupiter does one spin in 9 hours and 55 minutes. That's almost 10 hours. What have you done that was 10 hours long? Maybe gone to school. Maybe went to summer camp. But during that time you were in school or in summer camp, Jupiter did one rotation. Of course, Saturn's really fast. Earth is pretty normal because it's our planet and we're special. See, Mars is relatively about as fast as Earth. So when it comes to spin, they're pretty close. And this little symbol at the top corner, that's called an angle. And that's basically how the planet is tilted. So planets aren't just right up. They're always tilted. So what does the tilt of a planet cause for a planet? There's this thing that we experience throughout the year. Seasons, that's right. Because of the planet's tilt, we have seasons. And depending on the tilt, if the tilt's extreme, then the weather's extreme. If the tilt is extreme in the sense that it's compared to our planet. But we're going to focus on Mars. So can life form on Mars? Well, in order for you to have life, you need certain characteristics, you need certain features. You need heat because, let's think about it. Bacteria loves warm places. That's where they can thrive. They can feel alive, right? Put a bacteria in space where it's cold, it's not gonna thrive. What about water? I don't know about you guys, but I get thirsty sometimes. Water is really good for life. If you don't have it, then you get really, really thirsty and it kind of hurts you. What about hitching a ride? Well, maybe life doesn't have to form or start at a planet. Maybe it just hitched a ride on some space rock and just happened to be there. Okay, so let's talk about heating sources. So this first type of heat that I'm going to talk about is called primordial heat. So according to my parentheses, primordial heat is just heat from the beginning. And this type of heat is what you'll see whenever a large rocky object hits an even larger one. And when that occurs, it causes a lot of friction. So imagine rubbing your hands together like this. You feel a lot of heat, right? So imagine that at a planetary scale. That hand rubbing friction is what's causing the rocks to melt. And that heat stays with the planet, depending on the size. And of course, when a planet is hot, things that get hot, so think of ice. When ice gets hot, what happens? It melts, turns into a liquid. Same with rocks. And when you have liquid rock, all the heavier things tend to sink towards the bottom or the center of the planet. And that's how we're able to get an iron core. And all the lighter stuff, the rocky stuff we see on the surface, flows to the top because it's lighter, it's less dense. And whenever you have a planet that's hot on the inside, and then it starts to cool on the outside, we get these things called tectonics, which is basically the movement of rocks. The inside is still moving and it still wants to flow, right? But it's still protected by that outer shell. But that heat has to go somewhere. So eventually, it causes the rocks to move, and then we'll have these things called volcanoes. And that's when all the molten rock erupts to the surface. So let's think about it like this. Are volcanoes on Mars different than on Earth? What do you think? Yeah.
And while people are thinking about this, you got a question: will all the lava ever cool?
Ooh. Are you talking about for Mars or for a planet in general?
Shall I?
Yes. Okay. Planet in general.
Planets in general.
Okay,
yes.
okay. So yes, eventually planets will cool down. And the reason for that is because you only have a heat source for so long. Heat can be created through other ways too. And I only just mentioned one because the other ways tend to get a bit more complicated. Like, for example, there's this one called radioactive decay. And that's when radioactive elements start to, or isotopes, as they're called, tend to decay. And this decay causes heat as well. And this is actually one of the primary sources of heat for today for a planet. Now, you can only get that with certain elements. And certain planets actually, even though we're all made of the same stuff, cannot exhibit those type of phenomenons. And so in the case of Mars, Mars is actually half the size of Earth, which means that it was unable to create or maintain that heat. And so imagine, if you have like a little brother and you go outside and it's cold outside. Who's going to get colder quicker? Well, I guess when they're cold, and feeling cold is kind of a subjective thing, a personal thing. But your younger brother will probably get colder quicker because he's smaller. And when you're smaller, cold air or temperature changes happen quicker than when you're larger, because there's still more changes that need to occur when it comes to your temperature. So eventually, a planet will cool down. And then when it does, it just becomes, as the scientists call it, geologically dead, meaning that there's no activity, there's no volcanism. Kind of like the moon. And so back to volcanism, the atmosphere also plays a huge role in how high the volcanic eruptions can go. So, for example, if we have a planet that has a lot of atmosphere, or maybe even, a lot of atmosphere, maybe even a little bit more gravity, then you can see that a lot of the plumes won't go as high. And the plumes are what we see coming out of volcanoes. But if we have a planet or a body in space that doesn't have any of those constraints, then it can go as high as it wants. So we have this little GIF here, little video of this plume that's occurring where it's just shooting out into space. And it's just going as far out as possible. And this is probably tens of kilometers, probably like 30 or 40 kilometers, just shooting out far distances. So that heat's very important for life. Life loves volcanism. They can thrive in it, especially if they have water associated with it. So was there ever water on Mars? What do you guys think? Yeah, maybe. Yes. Of course there was water on Mars. Yes, and still is liquid water. Ooh. So actually, we do not have liquid water on Mars, and that's because we don't have an atmosphere on Mars that's strong enough or high enough for water to stay on Mars. So we can have solid water, and we can have gaseous water, but we can't have liquid water because temperature is too low and the pressure is too low. And we know that we've had water on the surface of Mars because we see evidence of liver, not liver, I'm thinking of water, lakes, and rivers. We have evidence of rivers on the surface of Mars from dried up riverbeds. So look at these patterns. If you've ever been to like a desert, you've probably seen something like this before. And even if you haven't, maybe go to Google Earth and you can probably browse around certain areas and see these remnants of rivers that once occurred. And they probably were filled with a lot of water. And of course, not all rivers are the same. They all form differently. But no matter how they form, they all contain one key thing, the potential for life. And if you were to look for life on another planet, you would want to look somewhere where there was once water. And the key places you would look are rivers. And of course, craters too, which we'll get to in a moment. But first, let's talk about glaciers. Glaciers are another way that we can find evidence of life. So there's something that when we get to the mineral part of our talk, we're going to start talking about, what is considered a mineral and what's not. Ice is one of those things that people would like to consider a mineral, but unfortunately cannot maintain its shape at normal temperature. So unfortunately, ice is not a mineral, but it does have the properties of holding evidence of past life. And we know this because on Earth, if you look at evidence, or if you go to museums that show mammoths or anything that was around the Ice Age ice would melt and would show these past artifacts, these past creatures, and they preserve their existence and they allow us to see it in the future. And of course, hitching a ride. So how would they hitch a ride? From space rocks, of course, that create craters. Now, there's one thing that I want to get across before we start talking about craters. The difference between a meteoroid and an asteroid. Now, a lot of people get those two confused because asteroids, they hear like, oh, an asteroid's coming, or an asteroid landed in my backyard. Those are not asteroids. In fact, if you were to compare a meteoroid, which is the actual thing that comes towards the planet, that becomes the thing that you find in your backyard, a meteoroid is probably the size of a marble compared to the asteroid, which would be compared to the size of a basketball, or even larger than a basketball. Maybe one of those big round bouncy balls that you play in PE. So always know that if we are saying that an asteroid's coming, it's probably going to pass by us, but it would be very dangerous for an asteroid to come to Earth. So a meteoroid it is. Now, what about when it becomes a meteorite? Now, when we talk about meteorites, we want to talk about the rocks that are from space, the meteoroids, and how they get to the Earth when they become meteorites. When they're in space, meteoroids, when the rocks are in space, they're called meteoroids. When they're shooting across the sky, you know, kind of like a shooting star, if you've seen one, that's a meteor, like a meteor shower. But when it hits the ground, that's when it becomes a meteorite. And a lot of minerals end with ite, I-T-E, to indicate that it's of the Earth. And this is an example of a meteorite. This one is an iron meteorite. So on the outside, you can't tell that it is one, but that's because it has this thing called a fusion crust. When you're going through the atmosphere, you catch on fire. And that's probably why we see meteor showers or shooting stars, because it's on fire. And it's basically going to get cooked on the outside, but on the inside, if we were to cut this, this would still be shiny and metally, like an iron meteorite. So once that meteorite hits the ground, then it creates these things called craters. And the reason why this is so important is because these meteorites could contain some evidence of life, or contain some sort of time capsule for a microbe to catch a ride and land on Mars. And when it does, it's out in the open. It can freely roam, and it can, well, not freely roam like chickens, but it can definitely get around, and especially if it's in a planet where there's water. A lot of these craters formed around the time when there was water on Mars. So it would make a lot of sense for these craters to be also filled with water. And these three combinations, the heat, the water, and the crater, create the perfect conditions for us to find life on another planet. Okay, does anyone have any questions before we get into minerals?
They do actually. They say, won't life die on the meteor after it hit?
Won't life die? So that's a very good question. It depends. So not necessarily, So it's possible that it could, but it depends on where it's located inside the meteoroid, essentially. Another good thing you could think about is the elemental compositions that could be used to create life on another planet. So maybe it's carrying the ingredients for life, and then once it's in the right conditions, so the water and the heat, then all three of those can create life. I can answer one more question before we get into minerals.
Any questions, anyone?
One more question before we get to minerals. All right. So, oops, went too fast. There we go. Minerals can capture life. Yes, they can. If you've ever heard of a fossil, then you know definitely that minerals can capture life. So we're going to talk about what minerals are, why they're important, and what is their connection to life. So what are minerals? Oh my goodness, I love minerals so much. It's one of my favorite things to study. So minerals are, by definition, a homogeneous, naturally occurring, solid, inorganic, crystalline substance with a specific chemical composition. So what does that even mean? So homogeneous means that it's all the same stuff throughout. So it would just be the same pattern of these three elements over and over and over again throughout an entire mineral. And naturally occurring, which means that we would go outside and we would just see them on the ground. We aren't making them in the lab. We're not changing them in any way. Humans aren't changing them. Nature is changing them. Solid inorganic crystalline substance. Now, solid meaning that they cannot be a liquid. So that's why ice cannot be a mineral. And of course, inorganic meaning that life can't make it. But here's the thing though, that definition is actually updated. Minerals can also be organic, meaning that life can create them. And of course, crystalline because they're made of crystals with a specific chemical composition, meaning that they have an actual combination of elements that we can identify to make this rock a mineral, which we'll talk about the difference in a moment between rocks and minerals. And the really cool thing about minerals is that they have like so many uses beyond just being really pretty shiny rocks. And one of those uses you guys might be familiar with if you like M&Ms is the little white stuff here, right? How they spell out M on the M&M. That's actually made from a mineral called rutilized quartz. And you might even think, oh, that sounds really good. That sounds really nasty. Like, why am I eating rocks? Well, guess what? We eat rocks every day. Do you ever eat a mill? You wonder how mills are so tasty? Salt. Salt is a rock. And it's a very tasty one, and we actually enjoy it too, because it has those properties that allows it to melt, and those flavors or the chemical combinations cause food to taste better, and we enjoy it, or preserve food too. Another key thing of preservation. So what's the difference between minerals and rocks? Okay, sugar, all right. So a lot of people use them back and forth, and they technically can be, in a sense. So when we say rocks, rocks are basically a group of minerals that form a solid material, a solid rocky material. And you can actually have just one element or one type of mineral in order for you to make a rock. So this is considered a rock. This is considered a rock. They're still rocks, right? But if you have more than one mineral inside of a rocky thing, that will be considered a rock. And there are three types of rocks. There's igneous, which means that it comes from volcanoes. So igneous. This is what you call it, a plume or a piece of I forgot what you call it. Ah, goodness. But this rock was formed through a volcano, and it's very light because it was formed in the air. Whenever all the stuff, all the powder, the pyroclastic plumus, thank you very much, plumus, it forms in the air and solidifies, and that's why it's very airy. There's metamorphic, which means that you have all these rocks on the surface, they go back underground, and it's experiencing a lot of heat and pressure, which causes it to change the shape of the chemicals or the elements inside the rock. And then when it comes back up, it becomes a whole different rock. And then sedimentary. And sedimentary are the ones that we're going to be talking about the most when it comes to looking at rocks on Mars to find life. And sedimentary rocks are basically just rocks that have been weathered, which means they've been exposed to rain, wind, who knows? And then they basically become, they wear away over time and they become a whole new rock. So why is it important to study these minerals or rocks? So minerals and rocks can tell us a lot of things. They can tell us about where rocks came from. How far have they traveled? You ever go out by the river and see some round rocks? That's because rocks aren't naturally round. They've traveled through water, and so they've been weared away over time. They became round. They also tell us about the environment that it lives in. So maybe those rocks contain fossils of plants or bugs, and that can tell us a lot about the ecology of the area. It can tell us about any changes that occurred physically within that region over time. maybe at one point there was they experienced an ice age there. Maybe it didn't. Or maybe there was a huge fire a long time ago and we have evidence of it. But most importantly, these rocks can also hold evidence of life. Now, it may not hold evidence of present life. It can though, but the past life would be also important too, especially if you're looking at organic minerals that are caused by the formation of life. So there are many ways that you can have rocks form on a planet. So on Earth, our favorite ways of thinking of how rocks form are through vegetation. And of course, here's a photo of how a rock can hold evidence of past life. So this is what we call an amber fossil. And what's that little thing inside of this amber? What do you guys think? It's a bug, that's right. And that's a very good question. Have you ever thought that we have rocks inside our body? Of course we have rocks inside of our bodies. Now, that's the part that I like to talk about, kidney stones. So I'm actually studying this particular mineral that I'm looking for on Mars, that on Earth, we know them as kidney stones. And they can form outside of the human body naturally, but if they happen inside the body, you're gonna have a bad time because they need to leave, they cannot stay. But vegetation, little bacteria, they also create these organic minerals. But what about on Mars? Like there's nothing on Mars right now that's organic enough to create these organic minerals. Well, that's okay, because in the past, we believed that that was the case. We know this because of all the riverbeds that we still see. And all that information, all that information that's captured by those rocks are still there to this day. But we need to know what type of minerals do that. Well, on Earth, we know that these minerals can do that. So do these minerals exist on Mars as well? Well, we found out that they actually do. But the tricky part is, well, how do we find these minerals? Well, that's when we start getting into using light to figure out this answer. So does anyone have any questions before we start talking about light shining us the way?
Anything unusual that you learned today about the rocks? Anything you want to ask about the rocks and minerals before we move to the next slide?
Because I can tell you right now,
let's
this is a mineral. And this is a very weird one that I like, called bismuth. And I just found out recently that this bismuth did not occur naturally. You can actually make minerals in the laboratory too. And these really, really pretty ones here are the ones that you'll more likely see. Sometimes you'll see them in the lab. Someone says a planet is made of amethyst. Ooh, speaking of amethyst, my own personal amethyst. It's my favorite. So pretty. And then you also have minerals like these. So this one is called vanadinite, and I kind of got it because it looks like a bunch of caramels stick together. You'll see that if you study minerals, you'll see a lot of rocks that look like food. Do not lick them. There are some rocks you can lick, but do not lick them until you know for sure that you can. Study Mars by comparing rock formations and composition to that we know on Earth. Of course, that's the beauty about being a geologist. Like, we have all the notes here, but at the same time though, we don't have all the notes. Sometimes we have to change the notes because of different ways that planets do their own thing. We're still learning how to be non-planetary bias. I'm sorry, planetary unbiased. Okay, so let's talk about how light can help us find life. We're going to talk about how light works with a mineral. And then we're going to talk about how satellites can use that light to find life. Okay, so how can light help us see minerals? So what do you guys think? How can light help us see minerals?
Let's give people some time to type.
Reflecting. Okay, very good. Reflecting. So yes, reflecting. So light can shine off an object. So like right now I have my lamp here, that's a source of light. And I can refracting, absorbing, spectroscope. Okay, everyone's already seen these slides. They know exactly what we're going to be talking about. So yeah, so the light's going to hit this object here. This is going to be my mineral. And then it's going to bounce off and it's going to hit my eye. And I'm going to say, yep, that's a mineral. That is very much a mineral. And we know that light can also be used, mentioned as heat and also as radiation. So whenever you hear the word light, heat, and radiation, they all mean the same thing. They all have to do with energy, right? And we're measuring that energy. So now it's like, so going back to the point of looking at a mineral and seeing it, looking at these images, is Mars really this color? By the way, these are photos of Mars. But does Mars actually have those colors on them? No. So actually, they do not, and they do at the same time. So these pictures have been enhanced to show these types of formations on the surface of Mars. So these little blue things, this is a particular type of silicate. I'm not quite sure off the top of my head what it is, but what scientists do is that they'll take a photo of the surface of a planet or just a planet overall, and they'll try to enhance the certain slight colors that might occur with that planet, just so we can see these mineral formations or any chemical reactions that are happening with that planet. And that's how we're able to manipulate how light works with an object. That's how we're able to see these minerals. But what about if we have an object that's, well, actually, let me talk about this first. So, of course, we have our light. It's hitting our object, but we're not on Mars to use our eyes to see what's happening. So that's where satellites come in handy. So we have the sun. The sun's light can reach the Martian surface. And once it reaches the Martian surface, it can reflect all of that light off of it, and it can go to our satellite. Now, the beautiful thing about our satellite is that it can pick up all that information and create that information to a way that we can analyze it and compare that information to other things that we're familiar with for us to know what the similarities and the differences are. And that's how we're able to identify things. So that light, that heat, that radiation is still energy. And that satellite is picking up on that energy for us to study. So why should we even use remote sensing? Which, by the way, that's what the study of using satellites to measure how light interacts with an object is called, remote sensing. Remote because we are far away from the object that we're studying, and sensing because we're trying to sense what are we looking at. So why is it important? You can find out what the surface is made of. So I can find out like what are you made of? Do you have copper? Who knows? I can learn about the origin of our universe by figuring out by using that information of what it's made of. I can see what changes have occurred on the surface. And also, I can find future landing sites and resources for future crewed missions to another planet, which is very important because there's no Starbucks on Mars. Okay, so now we need to talk about what type of light we're looking at, because light isn't just a light bulb. There's light that you can see and there's light that you can't see. And we like to use the light that we can't see to study our rocks. So which wavelength can you guys see? So there's radio, there's microwave, there's infrared, there's visible, ultraviolet or UV, X-ray, and gamma ray. So which one can you guys see? I don't know about you, but I think I can see visible. All right, got some visibles, visible, visible. Everyone's agreeing, visible. All right.
Isn't it amazing that we have other living creatures on this planet that see in a different spectrum?
Exactly.
Just a side note, yes.
Mm-hmm. Like, what can bees see? Bees can see in infrared, right?
Mm-hmm.
I believe so, yeah. Yeah, so scientists or geologists love to use infrared in order for us to study rocks. We'll get to that in a moment. But we can also use infrared to talk about, to study different things that are happening on Earth as well. So what differences do you notice about these two images? They're both the same though, by the way. The electrons and chemical makeup, that's very true. One is more visible. Okay. So the left or the right? I think the left one is the visible one. Now the right one, this one is looking at the Earth in infrared. And what that infrared is doing, actually, is that infrared? I think it's infrared. So I believe it's infrared, but I know exactly what technique they're using. They're using this technique to study the health of vegetation on Earth. And the level of red indicates if it's healthy or if it's sick or if it's not doing too good, if something needs to change. So what's happening when light interacts with the mineral? That's the fun part. So going back to what I was going to say earlier, we need to look at rocks in a different light in order for us to determine like if these two things are different. You may have rocks that look the same on the surface, like they're both white, but which one is which? They're both different chemically. So this is where light interacts with the molecules inside. And at the wavelength of infrared, we can actually cause molecules to vibrate. And these vibrations can be stretching, they can be like punching in a way, and then they can also bend. And so what happens is these things are absorbing some of that energy. And what's happening, and then after it absorbs it, it's going to reflect whatever things they did not absorb, essentially. Kind of like how we're able to determine what red is. We're able to determine red because all the colors, all the light hits this, but we only get red back to our eyes. Everything else is absorbed. So when you have our light and we have our mineral, we have spectra. And spectra is actually a wavelength that we're able to use with a graph to determine if they're absorbing that energy or if they're reflecting that energy or emitting that energy, giving it off. And so our rocks like to absorb that energy. And when we see an absorption, we see a little dip. And each rock has a very unique fingerprint that's associated with them when it comes to spectra. So if we see a certain dip that's happening in the spectra, we know, or a certain combination of dips, we know that that mineral is of that mineral. So for my research, and I'll try to make this as brief as possible so everyone has time for questions. So what I do is I have my Martian image, and by the way, this is my actual research. And I noticed some of the features that's happening. So this is actually along a crater. We use this red, green, blue combination in order for us to highlight different features of a rock. So for example, maybe I'm looking for a particular mineral group. I would make that red, meaning that if I see red anywhere in our image, that means that that mineral group is there. What if I'm also looking for some mineral that contains a certain element like iron or calcium? And I want it to also be a carbonate as well. Then that will come out depending on the combination of red and green, which is yellow. That will come out as yellow. And of course, I want that rock to be hydrated too, because I want to find life, and life loves hydrated minerals. Well, organic minerals tend to be more hydrated in a sense. And so when that becomes the case, then we have all three of our combinations, and that comes off as white. So do you guys see any white anywhere in the image? Some. Exactly. So it's not always going to be perfect, you know, unless we know for a fact that that mineral is there. Sometimes it's going to come off a little bit like a really light color. And so when it's as close to white as possible, that's actually pretty good because that indicates that it has a bit of those properties. Not all of it, but definitely close enough for us to start analyzing it. And once we start analyzing it, we look at each pixel. Now, this is just a video of me moving my cursor over my image. And these are all of the same image too, but I'm using my red, green, blue combination to highlight certain things. So as it's moving at each pixel, you can see how the absorptions change. These little dips. Oh, there was a little spike there, so that must have meant there was a dip somewhere. And here's another dip here as well. So I'm looking at those dips in order for me to figure out if that mineral is a mineral that I'm familiar with. And of course, these are the final steps. This is the steps to summarize everything. I put my characteristics or the things that I'm looking for in a mineral and a combination of colors, and then I get my map. Now, once I have my map, this gives me an idea of where to point my cursor to look at the pixel that will give me my spectra. And these little lines here match with the red, green, and blue. Now, these characteristics for carbonates, blue, they occur at this absorption. So I'm like, okay, so that is definitely a carbonate. But then the green, hydrated mineral, that occurs at this absorption, around this number. All right, a hydrated carbonate. Then lastly, I look at the red. That contains anything with iron or calcium. Now, of course, iron can occur in other places too in the spectrum. But in this case, I was looking for this particular region. And I was able to find my mineral. And these are just some examples of what you could also see when you use different combinations. Sometimes the map will come out like this. And honestly, I just love showing these photos because they're so pretty. The pretty part of science. A lot of people don't realize that science is more art than science. And this is very artistic. Look at this, you could paint this. But it's still informative too, because by looking at it, I'm entertained, and also I'm informed by looking at all the magnesium carbonates along the rim of the crater. You can also look at this image and determine the distribution of minerals, how it's spread out when the impact occurred. It's so crazy how geology does this. And of course, this information also matches with minerals that do contain life, that can hold life. And so, so just going through this very quickly, here's the last image, but to summarize everything, we use light to shine that information or shine a light on an object on another planet that can contain life based on what we know on Earth. And then that satellite gives us that information, that preliminary information. And this is actually really cool because if it's a nearby planet like Earth, then, I'm sorry, a nearby planet like Mars, then we know that, oh, wow, that's there on Mars? That's like right around the corner. Take us 9 months to get there. We know, we have evidence that life is, well, past life was there, but that's still evidence enough to show that we should go there and see if there's anything else that may have formed, or maybe we need to redefine how we determine what life is, spectrally, spatially, scientifically, chemically. But do know that this diagram is very simplified, but it's not always that easy to find life on another planet. We will need to change how we perceive life. We will need to redefine the meaning of life in a chemical, scientific way in order for us to really find out if there is life on Mars. So that's it. Does anyone have any questions? Is obsidian a mineral? Ooh, I love this question. So obsidian is not a mineral. It's a mineraloid. Mineraloid. And what that means is that, oh my goodness, what is it? So it does not have, what is it? Sorry, I've been studying for my qualifying exam, and this is actually one of my questions. So I know it's a mineraloid because it doesn't have the crystalline structure. There we go. It doesn't have the crystalline structure inside that mineral. Honestly, I should have grabbed my obsidian somewhere in the house, but normally with a mineral, you have some sort of crystalline structure at a molecular scale. And even from the outside, looking at obsidian, it looks like a mineral that could have that. But if you were to put that under some sort of microscope, or if you do like optical mineralogy, which is using a microscope on minerals, you can see, or actually not even that. You will have to probably use an electronic microscope or some sort of microscope that allows you to analyze the crystalline structure of a mineral. But when you do use that, you can see that obsidian does not have that crystalline structure. Therefore, it is not considered to be a mineral. Let's see. Based on your research, do you think there is/was life on Mars? Okay, so based on my research, I definitely do believe that there was life on Mars. It definitely had the mechanisms to have life a long time ago. And by a long time ago, I mean billions of years ago. We had an atmosphere, it had water, it had possibly vegetation, possibly. But as far as is there life on Mars is being present, well, that's a tricky thing to say, because superficially, if we were to compare it to what we think life is in a sense of Earth, we can say no, there is no life on Mars. But if we were to redefine our definition by saying, well, maybe there is life on Mars, we can't see it because maybe life doesn't like the things that we like. And that's something that we have to take into consideration when determining this. What will be the mission of Perseverance being launched at the end of the month? Oh my goodness. Okay, so Perseverance mission is to basically look for any signs or any chemical compositions that are conducive to life. And they're looking at Jezero Crater because Jezero Crater has a lot of carbonates. And carbonates are a type of organic mineral that is oftentimes created through biological organisms. Now, in the case of Mars, we're not seeing a lot of carbonates, and this is actually something that I'm answering from my research. Like, why are there not a lot of carbonates considering Mars's past? But that's a whole nother conversation. But with carbonates being in the past, forming in the past, where Mars was very hydrated and had the conditions for life, it is possible for us to find evidence chemically of any past biological creatures, whether it be microbes or who knows what, that may have existed in the past by looking at those carbonates. And Perseverance and ingrid carbonates. Would that be linked to like diatoms? Would that be linked to diatoms? So what is diatoms? What are diatoms? Are you trying to say diatomic elements? I'm not quite sure I've ever heard of diatoms before. Diatoms. Julia, are you familiar with what diatoms are?
I always thought that diatoms are little water plants. So, but I may be mistaken. I think we may ask the person who is a microscopic vertebrates. Yes.
Okay. So microscopic.
Can you find? I think the question is: can you find an evidence for some microscopic creatures living on Mars?
Actually, you can. You can find fossils of microscopic creatures, and that's all the more reason why Perseverance is so important, because even us planetary scientists who do remote sensing to look for these carbonates, we can find them all day and night, but we still can't find those physical structures that we would look for in those minerals that would show evidence of it in a fossil-like state. We can show where to look, but we can't definitively say that is life. No, you can find evidence. Okay. We find evidence in diatoms of paleo habitats of high plains and in the United States. Okay, nice. All right. So the reason why I was a little bit apprehensive about answering that is because I wasn't familiar with the word diatoms. So now that I know that they're just microscopic vertebrates, then the possibility of finding them on Mars is actually, it's definitely possible for us to find them, considering Mars's past. Could you make an atmosphere on Mars? Oh boy. So we know, okay, so the reason why Mars doesn't have an atmosphere now is because, and I'm going to get to that, can you make one in a second. The reason why it doesn't have one now is because Mars is half the size of Earth. And like I mentioned, like there's a lot of molten activity inside of a planet whenever it's heated. And whenever you're a planet that, oh, well, actually, during that heating process, it's also creating this thing called a magnetic field. That magnetic field protects you, me, and everything in the trees from being bombarded by solar winds or UV rays or any radiation that could potentially harm life. Now, unfortunately, Mars doesn't have that protection anymore because half the size of Earth, it lost its ability to create that mechanism because it started to cool down and all those rocks inside started to harden. And so when you lose that ability to create a magnetic field, then you lose that ability to protect your atmosphere, which is why Mars doesn't have that stable environment for liquid water to form on the surface. Now, it is possible for us to find it in the subsurface, but that's a whole nother conversation. Now, going back to Mars's, or creating an atmosphere on Mars, oh boy. So the reason why I'm thinking about this, because I actually read a few things about this recently about how you could potentially jumpstart Mars's ability to create an atmosphere, and it's super weird. I'm still need to read up about it, but it's like they can you can bomb Mars using some sort of I'm not sure what type of bomb, but like like a nuclear bomb or something like that, and you can like cause like the internal parts of Mars that's still relatively active to be active again, but it's not going to happen overnight. It's going to take, what was it, hundreds of years. Are you familiar with this, Julia?
Yes, I've heard Elon Musk was going to nuke Mars and make it warmer and also create some atmosphere. I'm not sure that the scientific community is very happy about it.
Yeah, like I'm not sure that's not a good thing at all. Like, what if there's life and then you just ruined it for everybody because you want to make it comfortable for humans? That's
exactly.
Yeah. What and what?
We got another question in private chat that's asking about lakes on Mars. Are there any lakes on Mars, and where you expect to find life, or how do you even look for underground water on Mars?
Okay, so there are paleo lakes on Mars, which is basically lakes that aren't like lakes anymore. And okay, I remember the last question was about, can you find water underground? And yes, you can. You can find water underground. And we actually have this instrument called SHARAD that's a part of the Mars Reconnaissance Orbiter. And what it does is that it uses, oh boy, what wavelength does it use? It has to use something, it uses like some type of sonar. It's not sonar. I can't remember. I want to say radio waves. That sounds about right. It uses radio waves in order for it to penetrate the ground of Mars. And it goes down about, I think, 15 kilometers, 10 kilometers, or maybe I'm being a little bit too generous with the numbers. But basically what it does is that it tries to find little pockets. And the wavelength knows what going through rock feels like. And so that's going to stay consistent until it reaches like an area where it's probably some sort of subsurface or subaquifer, sub ice place underneath the ground. And those detections or those vibrations, and I'm probably using the term incorrectly, but that interaction with that wavelength and that empty pocket will show up as some sort of, it kind of looks like an X-ray image, but you'll see these pockets where it's just like, oh, that's not solid ground. What could that possibly be? And how they're able to definitively state that that is water, I'm not quite sure. But the instrument is designed to penetrate the ground in order for you to find those pockets of water. And we've actually been able to detect it, I believe, twice. Once it's underneath the ice in the south polar region of Mars, but it's about a kilometer down, which, if you want to use that, for future humans, you would have to have some sort of mechanism to dig 1 kilometer underneath the planet, which time consuming and very expensive. So we're hoping to find something a bit more closer for us to study and use.
Well, it's about time for us. Miche, that was absolutely amazing. That was such a wonderful discussion. And you have such a gift of explaining complex things in simple language. It was a delight to listen to you.
I enjoy doing this. This is something that I want to do for the rest of my life. Talking about it and doing research are two favorite things.
Thank you. Thank you. It was amazing.
Oh, this is my favorite webinar. I'm so glad that you guys enjoyed it. If y'all are ever in DC, once we're all out able to visit and stuff like that, please go to the Air and Space Museum. We have this one discovery station about meteorites. It'll knock your socks off. It's out of this world, pun intended.
So do you actually work there as well right now?
Oh, I don't work there. I'm just a lead volunteer there. So I love going there just to talk to people about rocks, space rocks, and we even have a discovery station on spectroscopy. But we could talk about that too. But I actually have to log off as well. So
okay, well,
thank you very much, everyone, for coming.
Thank you. Thanks
Of
a
course.
lot. And I hope you will come again and talk.
Of course I will. Anytime you invite me, I will talk about Mars and rocks all day.
Yes, yes, great. Thank you.
Of
Thanks
course.
a lot. Thank you. Goodbye.
All right. Bye, everyone.
Bye, everyone.
Bye.
Goodbye.